method. Introduction. The idea of moment area theorem or moment area method was developed by Otto Moore and later started formally by Charles E. Green in 1873. It is just an alternative method for solving deflection problems. In this method, we will establish a procedure that utilizes the area of the moment diagrams, actually the M over EI diagrams, to evaluate the slope or deflection at selected points along the axis of a beam or frame. And what is moment area method? This is one of the easiest methods for finding deflection and slope of a beam with the help of area of bending moment of the beam, which is loaded with some load or any moment at any point or on whole span. When the superposition technique of indeterminate beam accelerated according to following reasons, restrained and continuous beams differ from the simply supported beams mainly by the presence of redundant moment at the supports, then the moment area method can be used. It is convenient to use this method with great advantage in the following type of problems. First, it is a cantilever beam or cantilever beams slope at the fixed end is 0. Number 2, simply supported beams carry a symmetrical loading, slope at mid span is 0. And beams fixed at both ends, slope at each end is 0. And for the deflection of beams, assumptions for slope and displacement by moment area method are as follows. First, beam is initially straight. It is elastically deformed by the load such that the slope and deflection of the elastic curve are very small, and deformations are caused by bending. So these are the assumptions for slope and displacement using moment area method. For the theorems of our moment area method, first, the change in slope between the tangents drawn to the elastic curve at any 2 points A and B, so this is point A and point B, is equal to the product of 1 over EI multiplied by the area of the moment diagram between these 2 points. So we have the load and the moment diagram. And from point A to point B, based on the moment diagram, the solid color blue is the area based on the point A up to point B. CG is the centroid of this area, and from centroid up to distance A, which is designated as X sub A, and from centroid up to point B along X distance or X axis and designate as X sub B. And the dotted line is the slope or the deflection, and this is the tangent line at A and another tangent line at B. And the angle formed from A to B, it is tangent theta or theta A sub B, and the proportion from at point B, we have the tangent line at B and tangent line at A. And the angle theta, which is theta at A to B, it is equal to 1 over EI and multiplied by the area from A to B based on the moment diagram. And for theorem 2, the deviation of any point B relative to the tangent drawn to the elastic curve at any other point A in a direction perpendicular to the original position of the beam is equal to the product of 1 over EI multiplied by the moment of an area about B of that part of the moment diagram between points A and B. And the formula for deviation from B to A, it is equal to 1 over EI times area of AB multiplied by the distance from the centroid up to point B, which is along x-axis, that's x sub B. And the deviation from A to B, it is equal to 1 over EI multiplied by the area of AB, and we multiplied by the distance from the centroid up to point A along x-axis, or x sub A. So these are the formulas to be used if you're using theorem 2 to find the deviation. And for the rules of sine, the tangent line at A and intersect at tangent line at B, from A to B, we form theta AB, and the sign is positive, which is counterclockwise. When A up to B, tangent of B, we can form an angle which is theta AB, and the direction in this example or in this diagram sign is negative, or it is clockwise direction. So rules of sine in this case, for counterclockwise, the value for theta AB is positive, and for angle theta AB based on clockwise direction from A to B, and the sign is negative. For the deviation from B to A based on the tangent line and vertical up to point B, the sign for the deviation from B to A is positive, and also for A to B, wherein the slope is counterclockwise or clockwise direction, the sign is negative, or the deviation of at any point is positive if the point lies above the tangent, and negative if the point is below the tangent. So this will be your basis. If the line from A up to B lies above the tangent, then it is positive, and negative if the point is below the tangent. So the deviation of any point is positive if the point lies above the tangent, and negative if the point is below the tangent. And measured from left tangent, if theta is counterclockwise, the change of slope is positive, and for negative if theta is clockwise direction. Process to calculate deviation. First, apply Theorem 1 to determine the angle between two tangents, and Theorem 2 to determine the vertical deviation between these tangents. And we realize that Theorem 2 in general will not yield the displacement of a point on the elastic curve. When applied properly, it will only give the vertical distance or deviation of a tangent at a point A on the elastic curve from the tangent at B. And then, after applying either Theorem 1 or Theorem 2, the algebraic sign of the answer can be verified from the angle or deviation as indicated on the elastic curve. So these are the process to find the value for deviation. Example, for the beam given, find the value of EI deflection at 2 feet from R2, and the diagram uniform load from point 1 up to R4 feet, and let's designate this A, this is point B, and point C. From point A, which is reaction at 1, or reaction 1, and at point C, reaction 2. From R2, we have 2 feet to find the value for deflection EI. So let's first find the reaction. So summation moment at A is equal to 0, and we can find the value for R2. R1 times 0, that's 0. And uniform load 80 multiplied by the length or the width or the length of the uniform load, that's 4 feet, and from the resultant, that's 1/2 of the length of the uniform load, that's 4 over 2, or 2, and clockwise direction to A, that's positive, and R2, and the direction is counterclockwise, so R negative R2, and the distance, that's 2 plus 4, that's 6 feet, and equate that to 0. And R2 is equal to, that's 80 times 4 times 2, that's 8, and we divide by 6. So 80 times 6, or 80 times 8, that's 640, and we divide by 6. And the least common is by 6, so 640 over 6, or in fraction, that's 320 over 3, and it is in pounds. And then summation of forces along y, and equate that to 0. And we have three loadings. We have reaction 1, reaction 2, and the uniform load. So reaction 1, so that's positive, and uniform load, that's downward, so negative 80, and multiplied by the length of the uniform load, that's 4 feet, and the value for R2, which is 320 over 3, and it is positive, so plus 320 over 3, and equate that to 0. And R1 is equal to, transpose negative 80 times 40, so that's positive. 80 times 40, that's 320. 320, and negative 320 over 3. And the value for R1, it is equivalent to, in fraction, that's 640 all over 3 pounds. So we have now the value for R2 and R1. So R1, it is equivalent to 640 over 3, and R2, that's 320 over 3. And to find the deviation of A to C, so deviation from A to C, T of A to C, that's 1 over EI, and multiplied by area AC, and the distance from X sub A. So these are the summation from A to C. 3 loadings, a reaction 1, a uniform load, and a concentrated load. And we will be finding the deflection at point B. First, we will determine the moment based on the reaction 1. So moment 1 is equal to R1, 640 all over 3, and multiplied by the distance from A to B, and that's 4 feet. So 640 times 4 all over 3, and that's 2560 all over 3. And to find M2, and M2 is designated at this point, so this is M1, M2, and this is M3. For M2, so M2 is equal to 320 all over 3 for reaction 2, and multiplied by the distance 2 feet, and this is 640 all over 3, and it is positive. And for M3, it is based on the second degree, and the formula for the moment for the second degree, so that's the uniform load 80, and multiplied by the length from A to B, so that's 4, and the resultant, and multiplied by the half of the distance of the uniform load, that's 4 over 2, or 2. So 80 times 4, that's 20, times 2, that's 640, and it is negative sign because the uniform load is in downward direction. Now we have the moment 1, moment 2, and moment 3. We can solve the area. So we will designate the triangle as area 1, this will be area 2, and this will be area 3. At area 1, for division from A to C, that's T A over C is equal to 1 over E, then the summation of area AC and multiplied by XA. First, for the area 1, so that's a triangle, so 1/2 of the length, that's 4, and the height, that's M1, or 2560 all over 3. And the distance of X sub A is from A up to the centroid of the triangle. And this is 2/3 of L. So 2/3 of L, and it is equivalent to 2 times 4, or 8 over 3. And this one is 1/3 of L, so 1/3 times 4, that's 4/3. So we will multiply X sub A of area 1, that's 2/3 of L, or 8 over 3. This is 8 over 3. Next, for area 2, and it is also positive, the height, or M2, is 640 over 3, and it is a triangle, so 1/2 and 640 over 3, and the distance is from B to C, that's 2, and from A to the centroid of point or area 2, that's 1/3 of L, so 1/3 of 2, or 2/3, and the distance from 8 up to the centroid of area 2, we will add 4 meters plus 2/3, and this will be 4 plus 2 over 3. And last, for the area 3, and it's downward, so therefore it is negative sign, and the formula for the second degree is 1/3 of base times height, and the base, or the distance or length, is 4, and multiplied by the height, or M3, that's 640. And to find the X sub A, the centroid of the second degree from the left, that's this is the distance is 3 over 4 of L, and this is 1/4 L. So from A up to centroid of area 3, so 3/4 of L, that's is equal to 3/4 of L, and L is 4, close parenthesis, and simplify, so that's 1 over EI, so 1/2 times 4 times 2560 all over 3 times 8, and divide by 3, this is 40,960, and divide by 3 times 3, that's 9. Next, plus 1/2, so 4/3, 4 to 12 plus 2, so 14. 14 times 2 times 640 divided by 2, so that's 8,960 all over 9 minus 2,560, and close parenthesis. 1,960 all over 3 EI, and that's the division from A to C. So let's copy T of A sub C, that's 8,960 all over 3 EI. T of BC, and it is equals to 1 over EI, and area BC, and X bar B. And for BC, it's only the triangle with reaction 2, or 1 over EI multiplied by 1/2 of the triangle, that's 1/2 of 640 over 3, and multiplied by the length, or the distance, that's 2. And X sub B is from C to centroid of the triangle, so this is 2/3, and TB of C, so 640 times 2 times 2 all over 2 times 2, 3 times 3, that's equivalent to 1800 all over 9 EI, and that's deviation from B to C. By ratio and and proportion, the big triangle T of AC is to the distance AC, and Y to distance BC. So this will be T of AC over distance length of AC, that's 6 feet, is equal to the ratio from B, that's y all over the distance from B to C is 2, and substitute the value for T of C, that's 8960 all over 3 EI, and Y is equal to AC, that's 8960 all over 3I, 2 over 6, and Y is equal to 8960 all over 9 EI, and that's Y. And to find the deflection at point B, so deflection at point B is equal to Y minus T sub BC. So Y, the total distance at point B, so that's deflection at B plus deviation of B to C. And the value for Y, that's 8960 all over 9 EI, and is equal to the unknown deflection at B plus TBC, that's 1280 all over 9 EI, and deflection B, so 8960 minus 1280, that's 7680 all over 3 EI. In terms of EI delta or deflection, so EI deflection at B is equal to 7680 over 3, that's 2560 all over 3, and it is in pound foot cube, and this is the value for EI delta 3, and that's the answer.